So I said in the earlier videos that mathematicians consider elliptic curves to be one of the most important objects in all of mathematics, actually. And they're cubic curves. And so why is there the obsession with curves of degree 3 rather than just any curve? So let's see. So let's take an elliptic curve. So an equation of this form. So y squared equals to x cubed plus ax squared plus bx plus c. Okay, so here is a graph of it. The graph you've already seen. XY. So the graph of it looks like this. It doesn't have to, right? There's another shape that is possible, but let's just concentrate on this shape for the moment. Cubic curve. You know, perhaps you've studied abstract algebra, perhaps you just know from your experience the operation of addition. You know that you can, of course, add numbers, right? That's how we first learned about addition. You just add numbers. And then if you took abstract algebra, you also know you can add polynomials. In fact, you can create various structures called rings or groups where you can have an operation where you take two elements, combine them, and get a third element, something called a binary operation. So you take two numbers, combine them, and get a third number. Okay? You can take two polynomials, combine them, so add them, and get a third polynomial. You take two congruence classes, you add them, and get a third congruence class. All this somehow has to do with numbers. Elliptic curves, so cubic curves, smooth cubic curves on the plane, allow you to add points in a very elegant way. Let me show you how. So I'm going to take 2 points on this curve, P and Q. Well, you're already familiar with this picture, right? P and Q. Okay? Now what I'm going to do is I'm going to connect them by a line. What do we know about that line from the previous lectures? We know that this line for sure intersects this curve at yet another point. Well, I can see this point right there. Okay, I will call this point R. And now I'm going to reflect that point with respect to the x-axis. And I'm going to get another point. And surprise or not, I'm going to call this point P plus Q. Now this is not our usual addition. I did not get this point by adding the coordinates of P and Q. Okay? How do I get this point? By this procedure. Take any 2 points, connect them by a line, get a third point of intersection. I'm guaranteed that third point of intersection because that's a cubic. And we know, we studied this in the previous lecture. If I take a line and intersect it with a cubic, I had 2 points of intersection, 2 points with real coordinates. I'm guaranteed to get a third one. Not 2 more, not 5 more, not 0. I get guaranteed to get exactly 1 extra. Okay? So I take this point and I reflect it down and I call this P plus Q. Now there might be something sort of some little voice in your head asking, why don't you call this P plus Q? There is a reason, okay? We'll get to this a little later. Just follow me on this and call this P plus Q. So maybe I can just like take some other points now. How about I take another point? Maybe I don't want to add P and Q. I'll take a point here and I will call this, what's about here maybe? P, Q, R, how about I call it S? Okay? And I'm asking, like, so where is P plus S? Think about it. Draw a picture by yourself. Pause the video here, and now I'll give you the answer. So I connect P and S by a line. I am guaranteed a third point of intersection. I'll call it T. Now I take this T and I reflect it here. This point right there, that's P plus S. Now you can continue this game, like you can just keep adding these points. What else could we add? How about I'll try to now add P and P plus Q. Okay, so I move this point S, I move this letter S here out of the way, and I try to add P and P plus Q. So I connect them by a line. It should give me a third point of intersection. Do you see it? Do you see it? Yep, it's right here. It's right at that point. I'm not going to give it another name because the picture is becoming difficult to read. This is P plus Q. Now I'm tempted to write it as 2P plus Q. You see, addition is not just a way to cook third element from two elements. It has to satisfy some properties, right? It better be like associative and stuff. In fact, because I want the addition to be associative, I do not call the third point of intersection the sum of the two. It turns out it doesn't work that way. The addition defined in such a way would not be associative. But if I take the reflection, you actually get associativity. It's not so easy to prove that this addition is associative. You need a little bit of algebraic geometry to prove it. But we're just going to take it on faith here. So I'm going to say this addition is associative. This addition is associative. Not so easy to prove. Right, so if it's associative, I can write this point also as P plus Q, so 2P plus Q. Interesting. So I could have gotten this point from doing 2P plus Q. So first P plus P. Oh, but how do I define P plus P? I mean, if I have a point, how do I add it to itself? There is no line that I can draw because I don't have 2 points, right? You need 2 points to draw a line, and you only have now 1. Well, you draw a tangent line. Okay? If you want to get 2P from P, you draw a tangent line. So I'm going to do it on a separate picture because this is now becoming too difficult to read. So how do you double a point? Again, here's my elliptic curve. All right, so I'm going to place my P over here. Just want it all fit into this picture, so I'm not going to just make it completely arbitrary. P. All right, and then I'm drawing a tangent line here. It intersects the curve at yet another point. Bum, 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 bum. And this here, this. This is 2P. P plus P. Isn't that cool? This is a completely new addition, something you have probably never seen before. It's an addition on an elliptic curve. What makes it possible, first of all, is that this is a cubic curve. Because when I want to define addition, I want to take 2 points and get a third one. So if I have a cubic curve, if I take 2 points, connect them by a line, I know I'm going to get a third point. That's our previous videos talking about how many roots a cubic polynomial can have and how it can intersect a line. Given 2 points, they have real coordinates, I connect them by a line, I'm guaranteed to get a third point with the real coordinates. Here, you say, oh, this is only 2 points. Well, but this is a double point, right? This point has multiplicity 2. So I am guaranteed to get yet another point of intersection, 2p. Look, once I have 2p, I can actually get 3p. How do I get 3p? You want to think about it? All right, so I'm going to show you, right? How do you get 3p? Well, you just add p and 2p. So you connect these two guys by a line. It's not going to look so good in here. Oh, maybe I'll manage. Okay, because this picture is not really perfect for that. That's better. Okay. All right. Okay. All right, I connected 2p and p by a line. Where is 3p? Do you see? Yep, you guessed it right. That's the third point of intersection. You move it up. This is 3p. What about 4p? I have two ways of getting 4p, and the addition is associative. So one way to get 4p is I do p plus 3p. P plus 3p, I connect these two by a line. I kind of hit it right, not necessarily, went a little bit below. Okay, but anyway, where's the third point of intersection? It's here, down here, drop it down here. This is 4p. 4p. Okay, now, you see my picture is not precise. I mean, this is when drawing a cubic curve precisely would be helpful. Of course, I just draw it on the board. I don't know that my curve is actually a graph of a cubic polynomial. Why? Because doing 2p plus 2p, I should get the same point. I should get 4p. Will I? I mean, I'm not so sure that I'm that exact. How do you get 2p plus 2p? Well, you draw a tangent line to 2p. Okay, so I'll try. I'm going to force it to work. Aha. Okay, so that's my tangent line to 2p. Went through the same point, dropping down here, gives you 4p. All right, so my picture isn't as bad as you might think. I mean, it's kind of worked out. All right, let me just summarize this again. All right, so at first I wanted to get 2p. So I draw a tangent line at p. I am guaranteed another point of intersection. I go down here, that's 2p. Now I want 3p. So p and 2p, I connect them by a line. Here's a third point of intersection. I go up with it, that's 3p. If I want to get 4p, I can get p plus 3p, so I can connect these two by a line. Here's the third point of intersection, drop down, 4p. Or I can get 2p plus 2p, so 2p twice. So I draw a tangent line to 2p, it intersects the curve here, drop it down, 4p. I strongly encourage you to go to GeoGebra, ask it to graph an elliptic curve for you. It's gonna graph it precisely, okay? And then pick points on it and add them and add them and add them as much as you can. It's a really fun thing to do, okay? It works, it always works because it's a cubic curve. So it's always gonna work. Except for one case, right? There was this case that we studied in the previous video when the points were on top of each other. What do you do then? What if I have a point P and a point Q and they're exactly on top of each other? So if I connect them by a line, I do not get a third point of intersection. Well, it turns out that the plane is really not the right way to view elliptic curves. The right way to view them is the projective plane. We're not going to introduce the projective plane here. This is not a course about elliptic curves. So we're going to use a fix that almost everybody uses to still be able to draw these curves on a plane and not on the projective plane, for which it is much harder to imagine what things are. there's just a simple fix that that you can make, and it actually works out very well. Namely, if the points are on top of each other, or if I just do a tangent line here at this point, which I give me a vertical tangent line, I am defining that p plus q to be infinity. Put infinity in these brackets. Okay, so that is an extra point that I introduce on an elliptic curve. So to be honest, I lied to you at the beginning. An elliptic curve is not just that, it's that plus an extra point at infinity. Wherever you have 2 points aligned vertically, then you just declare their sum to be infinity. It's interesting, it's actually kind of a bit confusing because we write infinity for that point because it's like somewhere there, right? We just think that the curve intersects the line again somewhere at infinity. However, for this addition thing here, infinity works like 0. That is, if I add infinity to something, I actually get the same thing. So, infinity plays the role of 0 for this addition. i.e., p plus infinity is p for any p. For any point, when I add this infinity to them, I get back p. All right, and then when you think about it, so that means that p plus q, when they are vertically aligned, they give me this 0 for this addition. So in other words, q is actually negative p. That's not a negative in terms of negating the coordinates. It's negative with respect to this addition. So this q is actually negative p, and this p is negative q. Right? This p is also negative q. Okay, I really urge you, go to GeoGebra. They'll give you a precise graph of an elliptic curve, then pick points and draw lines with a ruler and play this game, adding points, doubling points, and so on. Next time, we're going to actually derive formulas for coordinates of these points that you get by adding them. It turns out, not only this is a fun game, but it's actually a very, very profound game that you can play with these points. Namely, there's something about rationality of the coordinates that behaves really nicely when you do addition on an elliptic curve. And this is actually, this fact, again, we're going to talk about this in the next video, is what makes this theory so extremely important and interesting to mathematicians.